in one of the early scenes in The Graduate, the movie by Mike Nichols, with the wonderful Simon and Garfunkel music, Mr. Robinson calls Dustin Hoffman's character aside and whispers one word in his ear: plastics. Well, plastics had a lot to do with the hi-fi revolution of the late 50s and the 1960s. And the reason was that records, long-playing records, were now made on a special vinyl that could take a much finer groove and therefore reproduce music much better than anything that had gone before. The earlier lacquer records were very fragile and hard to press, and frankly didn't sound very good. The changes in the ability to record also caused there to be a revolution in things like the players for records, the tone arms, and, as we have seen in part one, the amplifiers that amplified the sound. I haven't talked about loudspeakers, and I don't plan to, but there was also a significant revolution in those areas. So if you remember, in part one, we talked about the Williamson amplifier and why it was such an improvement over everything else. In this part, we're going to move on from that to a couple of additional changes, one called the ultralinear and the other called cathode loading. If you watched part one of this two-part series, you know that we left off after having looked at the innovations that a fellow named Williamson made in high-quality amplifiers. This began in 1947 with this article. You probably will also recall that one of the improvements that he made was using a tetrode as a triode by connecting the screen through a resistor to the plate. Some of the other advances were in the transformer itself, and the particular transformer that Williamson used was wound by a company named Acrosound, who developed a series of transformers. Well, after the release of the Williamson amplifier, in 1951, two engineers from Acrosound published this article. This appeared in the Audio Engineering November 1951 issue, called An Ultralinear Amplifier. And what they did was discover a way to use a special transformer to realize the advantages of tetrodes. That is, the higher power, the higher plate resistance, higher amplification factor, without having so much of the distortion. You remember we talked about the kink in the tetrode's characteristic curve, and a number of tubes called kinkless tetrodes were developed, and the engineers at Acrosound developed a way of providing a separate transformer primary for the screen grid. And in essence, what they are doing is they are providing some of the output power from the screen grid. Now, you may recall that one of the problems with the typical non-ultralinear is that normally the screen grid is connected directly to B+, or the center of the transformer. And the current flowing from the screen grid does not contribute to the output. It's the loss of some of the plate current to the screen grid that causes both the kink in the characteristic curve and also a loss in efficiency. So the two gentlemen, David Hafler and Herbert Quiros, I hope I'm pronouncing that correctly. Let me show you the there they are, developed this new method of building transformers to help realize the efficiencies of tetrodes, or actually of kinkless tetrodes, that is essentially beam power tubes, by a slightly more complicated transformer design. So let's talk about that and the circuits that resulted. This is a chart that the developers of the ultralinear Acrosound engineers developers plotted based on the percentage of the screen tapped points. Now, let me explain what we're talking about there. You can have the screen tapped at the center of the transformer. That is essentially no screen tap. Or you can connect the screen through a resistor to the plate. That is basically triode operation. So what the Acrosound engineers were doing is they were saying, well, what if we don't do either of the two extremes? What if we tap in the middle, or 25% of the total, or 50%, or whatever? That's where this curve came from. And what they discovered was there was a kind of sweet spot here at about 50%, where you got pretty much the maximum power output and the least distortion. These are distortion curves. This is power output. So by choosing about a 50% tap point on the transformer, you can use a tetrode in tetrode mode, but at very low distortion and very high power output. So let's look at the circuit that they actually proposed. Here is the circuit from the original article, and you will notice that the transformer primary is tapped, and that the tap feeds the screen grid. The plate still is connected to 100% of the primary. The power supply is still connected to the middle of the primary, but the screen grid is neither connected to the plate nor to the power supply, but to a point 50%. That is halfway between the plate potential and the power supply voltage. So this produced a much higher power without sacrificing very much in the distortion. Now, like anything else in life, there's no free lunch. I admit that, and they admit in the article, that the so-called ultralinear amplifier is much, much more linear than the tetrode designs of the day. But it's still not quite as linear as a triode. So what they were doing was a compromise. But it was a very, very good compromise, because you see, one of the problems with the Williamson design was, although you were using a beam tetrode, you weren't taking advantage of its real characteristics. Instead, you were using it as a triode. That limited the power output. And one of the things that they discovered was power output was important, particularly in dynamic range. That is, a lot of music goes from very quiet to very loud. Consider the 1812 Overture with its cannons and drums and extremely loud sounds. And it's very quiet, violin passages and others. A lot of music, particularly symphonic music, is this way. Now, in HiFi, this circuit became very, very popular. And let's look at a design incorporating this that is an improvement even still on the ultralinear design. In June of 1952, Hafler and Kuros published this article in Audio Engineering about the application of ultralinear operation to the Williamson amplifier. This is the amplifier that they built, the prototype. So let's take a look at some of its characteristics and its circuit. Here is the circuit that the authors proposed for an ultralinear Williamson amplifier. And they point out that some of the changes, of course, one is the transformer here. Another is in the feedback network. The component values have changed. And if you want to get this article from Audio Engineering, June of 1952, you can look at the specific component values and some other things. It's a little hard to read in this format. But the article, I commend it to you. If you are having trouble finding this article, I'm going to suggest you go to AmericanRadioHistory.com. They have a complete collection of audio engineering. Well, I'm not sure it's every issue, but it certainly includes this one. So in addition to the feedback, there also is a change to the input resistor and to a couple of coupling capacitors. Other than that, it's basically the same Williamson design, and this particular design, because it could produce more power, really took over. And so in later stages of development, say the mid-50s on into the 60s, when people talked about a Williamson amplifier, most of them really were talking about this modified Williamson, in other words, the ultralinear Williamson. And especially if you see in the schematic this tapped transformer, that was the giveaway that you're dealing with an ultralinear amplifier rather than a true Williamson design. Here is an amplifier that uses the ultralinear that I built. This appeared in August of 1958, and I think, yeah, this was in I'm sure this was in radio electronics. That's where I remember. Yes, radio electronics. Once again, I think you can see that radio electronics was sort of my magazine. I subscribed to a number of them eventually, but the one that I really enjoyed and that really had a big influence on me was radio electronics. I read everything about HiFi in there. So here is the circuit, and you'll notice the characteristic tapped transformer. This particular one uses 6V6s, which were a little more readily available, particularly in the United States, than some of the so-called kinkless triodes or kinkless tetrodes. And so this is an amplifier that I actually built and used for some time. In that same year, 1952, a designer named Baxandall published this article on what is called negative feedback tone control. And I mention it at this point because this method, the so-called Baxandall tone control, once again became a staple of the Williamson ultralinear higher power HiFi amps of the day. So let's look at what his contribution was, and then we will move on and look at cathode loading. Here is the circuit that Baxandall developed, And I will only talk about this from a kind of top-down perspective and refer you to Wireless World, October of 1952, if you want to go into this in more detail. Once again, the Wireless World can be found on the same website, AmericanRadioHistory.com. So, what was it that Baxandall did? Well, largely up until this time, most tone control circuits were cut circuits. That is, you could cut the bass, you could cut the treble, but you couldn't increase the bass or increase the treble. And that was because, in general, they were just lossy circuits. That is, RC combinations that would take out the lows or take out the highs. What Baxandall did was, through negative feedback, he was able to provide a bass and treble control that could both boost and reduce. That is, if you move the control to the left side here, for example, on the bass, it would lift the bass. In other words, whatever the bass was in the normal configuration, the bass would actually get louder and the rest of the music would stay the same. Similarly with treble, you could lift it. You could also cut it. So for the first time, it allowed individuals to tailor the amplifier characteristics, where you basically set the volume for the mid-range, and then you could adjust the bass higher or lower than the mid-range, and the treble higher or lower. And of course, eventually this technique was expanded into what today we call graphic equalizers and other things. Of course, most of that kind of thing is done digitally today, but in its day, much more complicated circuits than this were developed that could lift or lower a band of frequencies using, in some cases, I think the largest equalizer that I ever saw had 15 frequency bands. That is, 15 controls that could be used to raise or lower a particular band of frequencies. So I bring this in because by 1953 or 54, a Williamson design with an ultralinear transformer and connections and Baxandall tone controls, negative feedback tone controls, had become sort of the standard of the hi-fi industry. One of the next changes was what was called cathode loading. To set the stage for this, whether you connect the tetrode as a triode or whether you connect it as a tetrode in the ultralinear, all of the power that's transferred from the tube to the speaker goes through the plate. Well, some engineers began to look at the question of whether they could tap some of the cathode power, that is, the cathode current. And so they began producing transformers with a cathode winding, and this is called cathode loading. You notice that instead of the cathodes going through a bias resistor to ground, they first go through one side of a transformer and then the bias resistor to ground. And this is, of course, the cathode bypass capacitor. What that did was it added power to the output from the cathode. Instead of the power that was being dissipated in the cathode resistor, is now partly contributing to the output. That not only boosted the efficiency of the amplifier, but actually they discovered that it produced a slightly more linear response because it made up for some of the deficiencies of the transformers that, regardless of what you do with the circuit, you're still limited by what are called the BH characteristics of the transformer. That is the flux and current densities. One of the amplifiers that used this technique was the Bogan DB15, and you can identify a Bogan. Well, you can identify a cathode loaded circuit by once again looking at the output. In this particular case, you'll notice that there is a winding. It's shown on the other side of the transformer, but it basically is just another winding that is used to connect the cathodes of the output tubes. This is a Williamson nonlinear design, not ultralinear. I shouldn't say nonlinear, it was very linear, but it was not an ultralinear design. It used the standard Williamson circuitry, but with cathode loading. A little after that, the folks at Fisher began to release amplifiers that included the ultralinear design, that is, the screen grid connected to a tap on the primary, and cathode loading. You'll notice that the cathodes in this case are loaded through this. This was used, for example, in the Fisher 70A. At this point, the number of designs and modifications and so on really became almost a marketing competition. For example, Macintosh had a somewhat unique output circuit in which they cross-connected the screens. So instead of the screen being connected to the plate of the same tube, it was cross-connected to the plate of the opposite tube. Macintosh claimed that this produced more linear results and other things, and once again, it was one of these things that they, of course, had some technical data to support their claim, and some of the competitors said, well, it really isn't any different than the others. There are some advantages to this, or at least there are some technical advantages I won't go into having to do with phasing. But another addition that you may see if you ever work on any of these old amplifiers is what's so-called Class A2 operation. And this was used in the Fisher 50A. Class A2 allows some grid current to flow, some control grid current to flow. They use a special bias circuitry to regulate the bias on the tubes. By regulate, I mean it's dynamically controlled. And by doing so, they are actually able to draw limited amounts of current to the control grid. And once again, the Fisher engineers believe that this produced a better result. Once again, by this time, we're talking about almost the mid-50s. It was a lot of the technical issues had been solved, and while transformers continue to get better, circuits continued to be improved. The improvements were, well, frankly, in my opinion, marginal. And about the time that Fisher began to use this type of circuit, and Macintosh, the one above, is about when I found that this can be a very unsatisfying business for people. I wasn't actually in the business, but I was employed as a technician at the time. And I had a bad experience because I got into a situation with a bunch of people a whole lot wealthier than me who considered me sort of their expert, and their HiFi system was their status symbol. Well, I won't go into the details, but at any rate, I very quickly had to find a way to get out of that, and so I did. I went back to engineering school to finish my bachelor's degree. So I hope that you've enjoyed this overview of HiFi amplifiers, of the late 40s and 1950s. Most of these designs were continuing to be built into the 60s. Of course, by then stereo was starting to take over, but basically all stereo did was add a second channel. The circuit designs underneath were the same. So for example, an ultralinear amplifier now had 4 tubes instead of 2, one pair for the left channel, one pair for the right channel, and so on. There's also a lot of stuff I left out having to do with preamplifiers, and except for the Baxandall tone control, a lot of the circuit development in the preamplifiers for phono and later tape and other media were also interesting, but they're a little beyond the scope of where I was trying to go with this series. So I hope you've enjoyed this, and I hope that maybe in the future we can do something along these same lines. But for now, have a good day, and thanks for watching.